Hello, everybody. Welcome to our second project for our big data class that we taking this semester with Dr. Han. Now we get to work with two of my best colleagues that we have in class, Jose and Juncheng. It's definitely my pleasure to work with these guys. These guys did absolutely amazing, beautiful jobs here on part two. But I'm gonna kind of start introduce myself really quick. Michael, but everybody call me Mikey. Mikey Liang is my fourth year, also the last year here at Baylor. Taking this big data class. Now it's towards the end of the semester, but we're a pleasure. It's definitely absolutely amazing time to work on these projects that we learned during class that talk about DNC and all that cool stuff. But I'm gonna hand it over. Jose, why don't you introduce yourself real quick so that everybody know you, what you did on this part of the project.
Hey everyone, so my name's Jose, and so one of I guess the main part that I worked on was kind of part two. I was essentially just running like four different types of deep learning models, but it was basically using two types of optimizers, the Atom and the SGD, and then just trying to see how they would run with like less like or I guess like what's the right word? Sorry, I'm zoning out real quick.
MSE, the less more accurate or with less noise
No, layers. Layers is the right word I was
layers.
looking for.
Yeah,
Yeah, so I ran it with four layers, and essentially, kind of the main goal with that was just to be able to compare it to the second part that was done by other group members. But yeah.
totally. We're gonna come back later. Jose, you can explain a little bit more about what you did, but you did a great job here. Jincho, why don't you introduce yourself as real quick as well?
Yeah. Hello, my name is Jun Chen, and I worked on part two with Jose, and I ran all the models on 7 layers, and I did again for on the PCA data.
Definitely. Thank you, Jincheng, for doing that all that part. I know the 7 layer part, it was such a headache part. It takes forever to run. So you guys did a great job here. But I'm gonna start off. So what I did, my first part of this project, we're gonna jump right in. So I'm kind of just explain you guys what are some of the newest machine learning method that we learned here. The first one, the deep learning deep neural network here is definitely one of the greatest machine learning methods that we have here. It's great that handles big data really well, but if of course it has some cons as well. But whenever I talk, go through this PowerPoint, I'm gonna kind of explain y'all, hey, what are some the good part about different machine learning method, and what are some of the disadvantage of these models here. And second one, we have the seeing, and seeing is kind of a little similar to DN, but it does a great job processing image data. And whenever we're using these different models, we are choosing different layers. There are different neurons you guys pick, and there are different loss function. And whenever you're dealing with these different data sets, you kind of want to choose the right amount of layer or the right amount of neurons. So whenever we get to see them in real data sets here. And then another one here, long short time memory. This is also a kind of it's this we say this one is the RNN recurrent neural network. It also have some advantage and at the same time some disadvantage here. Extra tree is also a machine learning method that we have. This one, whenever I'm doing this project, I got confused a little bit. It does not. I was trying to plot a loose function or loose paragraph on this model, but it didn't work off. It didn't work out because it's a totally different thing. It's not even a narrow network kind of model. So we're gonna explain more in a little bit. And then we have one of the most important um, that score that we're gonna have here. The first one, the mean square error. Why we're using this one? So whenever you're doing a machine learning method, you have classification and also regression. MSE is a great measure for whenever we do regression. And of course, we have another one, which is R2 score. R2 score is the range from 0 to 1. It's pretty much predicts how well this method, this model fit our train data and our test data. So whenever this number gets closer to 1, it's doing a great job. But of course, you don't want to be 0.99 or too close to 1, because it may have a run into an overfitting problem. Whenever we're dealing with these data, we run a lot of times, we're modifying these different layers, we're modifying different neurons, we're modifying different parameters, just try and get better, the lower MSE and also the higher R2 score here. And now let's get a look at our first data set that we're dealing with right now. The first one, optional data. This one, let's look at the some of the column and also rows that we have here. This is one of the function we called earlier. Looks like optional type. Over here it says optional type is coded as 0 for call and put 1 as 1. So this is one of the important feature that we're handling with whenever we're doing this DNN and CNN. So pretty much, you get to choose different features and also one target. The target we're picking today is we're doing this implied velocity. And then in the beginning, when I first look at the data set, you're kind of confused. What are we doing? But whenever you kind of dig into more and play around with different models, you kind of figure out, hey, which one should I pick? See all these optional price, stock price, volumes, and time. These are just some of the important features that you don't want to filter out. And then we have also some of the call options here, the OTM, ITM, and ATM. We're going to get back to these later because we're going to split the whole data set into 3 different types, and we're going to see which model predicts the best. And then these are the features and the target that we have here. As we can see, target, that's just our one of the target we're trying to predict today. So now these are definitely some of the best graphic that we worked on. Some of the results. The first one, let's look at it. This is the MSE score for DNN model. Of course, whenever we're seeing MSE and R2, we're talking about regression. So look at this, really low. It's getting really low. The loss, as we can see, a smooth graph, and it's not overfitting because you can see they're doing their perfect job. And also R2 score, as we can see, 0.7. That's a great R2 score. It's never overfitting. It's never too low to predict. And then we have in the second one, the CNN model, as we can see here, 0.76, a little bit lower than DNN, but hey, CNN is good at dealing with graphic data, but this one is not as, you don't see graphic here, but that's reasonable. Also, we have here the long short-term memory. It didn't do a great job. Also as same as the MSE, it's a little higher than both CNN and DNN. And also we have the last one is the extra tree. We have all the different scores I'll put here. And then it's just some of the conclusion that we have here. Compare our DNN and CNN. Extra tree didn't have much the loss curve and nature, but some of the DNN has higher score, of course, but we're going to get back to these conclusions whenever we finish the whole data set. And then we have another prediction. So the first graphic we're looking at, this is the original data set. This is the whole data set we're doing this prediction. And then the second part, we're going to split this data set into only OTM data. So we're going to extract the only OTM data, see how our machine learning method, our DNN, CNN, they did it. Look at the score. So DNN 0.81, that's slightly better than our whole data set. As we can see, whenever you're putting OTM, you kind of did a better job here. Let me just move this down real quick. Same as CNN, look, this one even did a better job than DNN. And same as long short-term memory, they all slightly kind of did a better job than the whole data set here. And then, of course, with the OTM, we're gonna split the rest of the data set as non-OTM data set. Let's look over here. Isn't that kind of funny? 0.64. This one looks even lower than the original data set, and that just kind of gives you the feeling, hey, how's this data set feels like? And now I'm gonna jump back into, let's look at what are some of the ITM, OTM, ATMs. So these, whenever you're handling these different prices, and then you're gonna pay attention to these different out of money, in money, and out of money. Whenever you're doing machine learning methods, now you know, hey, which one, what am I doing? Which one, should I choose? Which will fit best? And of course, the last part that we have here is our European optional data set here. This one is a little different. Different as you can see on the first row here. The first line, the features, it has so many different things. And of course, target we're doing the same regression over here. Definitely not as much of observations, but it definitely have more columns here. I have a and also, yes, those are the graphics that we have here predicted our European optional data set. We can see here, CN did a really good job, but DN did not doing a best job here. That's some of the reasons that you're thinking about. Maybe it's something to do with the observation because it's not that much. Whenever one of the pros about all these neural networks is the bigger the data set, it kind of know a general pattern how these data sets are like, and they tends to do a better job on bigger data. And now these are the conclusions I hear. DNN, it didn't do a best job. It has a high MSE below the R2 score here, and CNN is pretty good at the accuracy is pretty good. And same as long short-term memory and extra tree here. Actually, as we can see here, it has the best R2 score that we have. Overall, as we can see here, actually really stand out. It's the most effective. And then we have our, deep learning models. We're comparing our CNN. It prefers a little bit better, closely to our long short-term memory. And of course, DNN is kind of it's useful, but we wish we have more observations that we have for this European optional data. And now we're gonna head it over to Jose, and you're gonna why don't you take over, explain us what you did this part, and what are some of the insights that you dig into from this big patent data.
Okay, sounds good. Yeah, if you can, I actually can't share my screen.
Oh yes,
disabled.
yes, my bad. Let me stop sharing my screen so you can share your screen.
It says the host disabled participant screen sharing.
Okay, let me see.
I don't know. That's something you can change quick.
Yeah.
If not, I can just bounce off yours.
Okay. See if you can do it now.
Okay, yeah.
Okay, cool.
Okay, so yeah, so essentially on the second part, it was over like the big patent data, and the biggest I guess the biggest thing that we were trying to predict with that, it was considered a high value or low value patent. And we did the traditional 80-20 split for the data sets from the training to the test data. Initially, I did my part, which was the 4-layer version, and then we redid it again to try to compare results with 7 layers. And we tested 3 different types of deep learning models: a deep neural network, convolutional neural network, and LSTM. And then within that, we did 2 optimization methods, ADAM and SGD. So just to go over the data really quick, there was really 32 main features, and then the class ID, which is what we use as a target variable for being high value or low value data. And then initially ended up doing kind of like tries to do like a feature importance score to see like if any of the features kind of stuck out automatically. And with that, feature 28 stuck out with having like an 79% like importance score, which was like really, really high compared to all the other ones, because the second one was only like at about 4%. So initially the goal, what I was going to try to do was like test it without this feature, or first test it with the feature, which is what we did. And then without it, we didn't actually get to that point. But I do think that's something very interesting, because you kind of looked at feature 28, even though we didn't have like what the variables were called specifically and what the data represented. It had like about a 95% correlation with the class ID. So it was like, so I guess it would have been interesting to see why that was the case. And then, so on our data set, we did like PCA, so way to kind of transform our data into like a low dimensional dimension. And then with that, we kind of ran like a little kind of different levels of interest, see how many components capture like how much variance relative towards the PCs or like kind of the axis. And we ended up going with 24 dimensions because that captured about 95%. So and you can kind of see that here. And then for the first model we ran, it was with the Atom Optimizer. It was just 4 layers, mainly focused on the ReLU activation function. And then once we kind of ran our results, it had a 99% accuracy, and all other scores were really, really good too. I guess the one thing with this is usually after like going through one time or twice within like the first 2-3 layers, it didn't really improve that much. You maybe like we would already be at like 99-98%, and it kind of varied depending on which model we ran, but it almost started being like we started running it for like up to an hour or even more without like really increasing our results. And you can kind of see this here with the epochs kind of representing just different layers, just how much times we reran the data. So within the training validation, specifically on the Atom, it didn't perform as good, but if you look really, really good, this can be a little misleading because even at the bottom end, it's like 0.993. So you can kind of see right off the bat, we started like a really, really high success rate. But compared to some of the other ones, this is like technically one of the worst performing ones. And then this was just running the same one again, but we used a different optimizer, which essentially kind of just changes some of the parameters or the way the weights get calculated during the neural networks. And as you can see here, this one also had like really high success rate. It did a little bit better on the overall accuracy, but it did a little bit less on the recall, which kind of means, I guess predicting the zeros, that's kind of where it did the worst. And but overall as a whole, you can see here it still did pretty good, but it did take it a while. Like I guess I'll have to start in and do as good, but towards the end, they all basically had the very similar results. And then the next one, we ran a convolutional neural network, which with the Atom Optimizer of 4 layers again, we got like near perfect results, 99% accuracy. And then if we look just at our training loss and accuracy scores, these were a lot closer to each other. I would say this is kind of one of the worst ones, but even then, like I said, like their scores were just so good that I guess you can consider maybe overfitting it. We tried it on different type of data just to see how it actually performed there. And then finally with the SGD again, the results were really good. The one trend that we kind of kept noticing was the fact that when we try to predict the zeros or the low value patterns, that's kind of where it would kind of do the worst. But even then, this was kind of one of the first ones where we kind of started noticing, like towards the tail end of like going through like about 50 layers, it kind of started dropping a tiny bit. But I guess it's hard to say if that trend would have continued. And then finally, with our last model, when we ran the Atom, it also performed very well. The F-score kind of signaled that as a whole, maybe it kind of didn't perform as well early on, which we kind of see from here. This is kind of one of the worst ones that kind of took a while to train. It kind of was more on the 95% accuracy compared to some of the other ones. But once it started going through more and more sequences of data, that's kind of where it started to shine. And then the same could be said here with the SGD optimizer version. As you can kind of see, kind of early on, it kind of performed a little bit worse. With this one, though, we kind of ran it 20 times just because it was one of the models that took the longest, even though the other ones were kind of going over an hour. I was able to speed it up a little bit by changing the activation function to like the hyperbolic tangent. So I guess that's something that maybe we should consider too, is kind of how the activation functions can process kind of different types of data a little bit better. And then for the second part, it was with the 7 layers, and
Yep.
I want to share my screen.
Sounds good. Sounds good, Jose. Before you end your sharing your screen, hey, why don't you explain us just a little more about our the optimizer that you used and the Atom and the SGD. What are some of the pros or what are some of the cons that you run into, or some of the conclusion that you can give us?
Yeah, so I guess kind of I would say it's probably a little bit harder to say with these just because everything was like really like close together in terms of kind of the scores. But
Right.
usually like the Atom, for example, it tries to go a little bit more off pure statistics and goes off like kind of using like the second momentum, third momentum, and I guess essentially it's just kind of like the derivatives, then the second derivative, third derivative type thing. And I guess the biggest thing with that is just kind of changes how the weights are a little bit more, and just kind of the hyperparameters as they go kind of layer by layer. But I guess the biggest results that we saw, it generally seemed to do a little bit better with the Atom. But yeah, I mean, I feel like it's kind of really hard to say, just because like everything just performed so good. They were like already at like 99% all of them.
Totally.
So
Totally.
I think the biggest comparison was be with like maybe if we started going like even like 400, 500 times the data. But
Sounds good. Sounds good. Thanks, Hilde, for all the hard work, and it was amazing. Juncho, you're an expert at picking the optimizer and all the theological. So I've heard isn't that the Atom is good at doing overfitting. It kind of not good at it avoids overfitting. What are some of the insights that you can give us comparing what are some of the pros of SGD, and what are some of the pros of Atom, and what are some of the disadvantage of them?
So I think SGD is like more robust to like overfitting.
More I see more robust overrating. See,
Yeah.
okay, that's see. Whenever we're taking the class that a lot of times there are theological pros and cons, but definitely these real world data sets is where we get our hands-on experience, hands-on practicing, and we can draw these conclusions. Or are they are actually good at doing things, or some of their disadvantage. But of course, Jose, thank you so much again. Juncheng, yeah, you can take over now. Share what share us, tell us what you did on
All
your
right.
part, and some of the cool things that you find.
Can you see my screen?
Yes.
Okay, firstly we have 7-layer deep neural network. And for this model we have 7 like dense layers with activation ReLU. And here's our code for the 7-layer convolution neural network. And we have 2 convolution layers and 1 polling layer and 1 flattened layer and 2 dense layers, and then drop out then the output layer. And here's the code for 7-layer LSTM. And we have 3 LSTM layers and 3 dense layer and 1 output layer. And here's the result for 7-layer DN with SGD. And everything got it like 100%. And all the lines are very smooth. And here's the 7-layer DN with Atom. It's very similar to the result that Jose has, but all the numbers are really good. But the Atom is like a little bit more volatile, I would say. And here's the 7-layer CN with SGD. It's almost like a straight line, almost. And same thing here, 7-layer CN with Atom, everything 100%. And it's a little bit worse than SGD. And here's the 7-layer LSTM with SGD. Here's 7-layer LSTM with the atom. I think everything for all three models, the results are the same, except the graph on the training and validation. And then we did PCA for big pattern data. We chose n components of 24. It kept 95% of the explained variance. And here's a little PCA visualization for the big pattern data. And here's the results. We ran all those models with SGD and Atom under the PCA embedding, and the results are quite similar. And here you can see that Atom is more volatile than the SGD under PCA as well. And here's the convolution neural network with SGD under PCA. Here's the result for 7-layer CN with Atom under PCA. And here's the result for 7-layer LSTM with SGD under PCA. And here's the result for 7-layer LSTM with Atom under PCA. This one, Atom did a little bit better job. So to conclude, in this part, we used DN, CN, and LSTM to do classification for the big pattern data set under a 20 to 20, 80 to 20 partition. And we checked all the classification measures from the report. And we increased deep learning models with at least 7 layers. Then we did PCA pre-processing before the DNC and LSTM and compare results. And for most of our models, we achieved 100% accuracy. However, most plot on the loss in accuracy with Atom is much more volatile than the ones with SGD. I think the training of the big pattern data, Atom's approach to adjust learning rates can lead to more fluctuations in the training process compared to the more steady approach of SGD. Thank you.
Sounds good. That was awesome job, Juncheng. Before we went into this call, I just want to ask a quick question, Juncheng. You designed the seven layers here. How long did it take to run for the whole project, or each epochs, or how many times that it take?
So I used GPU in Colab, and I think the average it was like 15 minutes for
15
each
minutes.
one.
You said
And for LSTM is a little bit longer.
For just
Yeah.
one visualization here.
Yep.
That's amazing. See, you did so many. There are so many beautiful graphic that we have. It took you a long time to run all these big data whenever you're doing DNA. And now now we're only handling this smaller portion of the data set, or small data set. Whenever we're going into the real world data, we're gonna use powerful GPU to speed up all the procedure. And definitely DNA is definitely one of the most advanced tools that we can use, but it just takes so many time. It uses so much resources. Before I end this call, Juncheng, you're an expert. See, you did a 7-layer. That was an amazing job. Why don't you go back to the slide that shows that 7 layers? Just kind of give us a little go through what are flattened layers, as we learned earlier. Hey, what are these different layers? What it does? Because these parts are really interesting. When I look at those, we're all data scientists. We're pretty good at those stuff. But whenever whenever who's watching this, or they're gonna be worrying, hey, why would you want to choose those? And why don't you share us what you did here?
So basically we just have like 7 like fully connected layers for this part for the DN. And the last one, last one is the upper layer. Two means is like doing like a binary like classification. So two means like two classes. And the softmax is like for classification purposes. So on the other hand, if you're doing like regression, you just change this activation to like linear or something.
That's amazing.
And for this convolution neural networks, is a little bit different because it has like partially connected layers and plus some like fully connected layers. So in this case, we have like two convolution layers and one polling layer and two fully connected layers.
So Juncheng, you said the polling layers. Can you explain us what are some polling layers that you can choose? See, now here you choose max polling, and also I know we have an average polling. What are some of the difference between why you choose max polling?
Because max pooling is like good for like extract the most like significant features.
Sigma
And
feature.
as part we did like max pooling 1D because the data is like it's like a tabular data and it's not image data, so we use 1D instead of 2D. And here for the convolution layer, we also use 1D as well.
Totally, that's awesome. And also you have here on the third line here, you have the flatten layers. See, we are quite confident about the flatten layer. Why don't you tell us, hey, what it does and why would we choose to use the flatten layer here?
Flatten just take a multi-dimensional data and flatten it into a like a one-dimensional vector, and it doesn't take any input, so just add it.
That's awesome. And also the dropout is as we've been learning dropout, it does it's robust to overfitting. Is that true? And did you run into any problems or did you feel, hey, this actually does its job? Or
Yeah, I haven't compared the model with and without dropout option. So from what I learned, it reduces like overfitting if
that's
you have
awesome. That yeah, it does a reduced overfitting. That's a great job. Absolutely amazing job on this 7 layers. And when I look at it, that's a great job that you did here. Thank you so much, Jin Chung. We're running out of time here, everybody. But before we end this call here, does anyone have any question that before I end the call? No, sounds good. Sounds good. It's definitely absolutely my pleasure to work with you guys, that Jose and Juncheng. And I wish that we have more time that we can tell you a little bit more about our what we did here. What are some of the conclusions? But don't worry, guys. We're gonna come back. We still have another semester here at Beta. It's absolutely my pleasure time to get to study and to get to work with all these colleagues. And thanks for watching. And I'll see you guys.